Hello and welcome to this lesson for OCR A-Level Physics on Module 6, Particles in Medical Physics, in the topic of capacitors and on the concept of parallel plate capacitors. So if we've been successful and we've learned in today's lesson, we should be able to know the definition of relative permittivity and the dielectric constant, calculate values of capacitance using dielectric action, and understanding the effects of capacitor dimensions in calculating capacitance. So we're going to be looking at the following part of the OCR A-Level Physics specification, 6.2.3, Uniform Electrical Fields. Now a capacitor is a device which stores electrical charge. It has capacitance. Now a capacitor consists of two conducting plates separated by a gap. The charge imbalance on the plates produces a uniform electrical field between them. Now the gap between the plates prevents the electrons from moving between the plates. This creates our charge imbalance over the two plates. This charge imbalance causes the plates to be attracted to each other, and this produces the electrical field which allows electrical potential energy to be stored. Now it also means that this charge imbalance leads to two plates that are equally but oppositely charged. Now to maintain this attraction, electrons cannot travel from the negative plate to the positive plate. Therefore, the two plates must be separated by an insulator. Now, if the insulator between the plates is air or a vacuum, we state that the charge stored by the capacitor is Q0. And also, if the insulator between the plates is air or a vacuum, we state the capacitance of the capacitor to be C0. Now, we can increase the capacitance or charge stored by placing a greater insulator between the plates. This is because there is less of a chance of the electrons travelling between the plates. We call this material a dielectric. Now, if the electrons do travel across the dielectric from plate to plate, we say the dielectric is broken down. This means the capacitor can no longer store charge. Now, examples of common dielectric materials include wax paper and polythene. Now, the increased capacitance of the capacitor after dielectric material is inserted is given as C, and the charge of the capacitor after the dielectric material is inserted is given as Q. So the effect of adding dielectric material to a capacitor is called the relative permittivity, or ER. Now, permittivity is a measure of how difficult it is to generate a uniform electrical field in a certain material. Now, the permittivity of free space is how difficult it is for a vacuum to generate a uniform electrical field. This is a physical constant in the universe, as is the same everywhere. Now, the value is 8.85 times 10 to the minus 12 farads per meter. Now, relative permittivity is how good a material is to generate an electrical field compared to how well free space generates an electrical field. So relative permittivity is calculated by the equation Q over Q0, C over C0, or E over E0. Now this value has no units, as it's a comparison showing the effect of the dielectric. The higher the relative permittivity, the better the insulated the dielectric material is. Now you can see here some examples of dielectric materials and their relative permittivity. Now another name for relative permittivity is the dielectric constant. Now the dielectric constant of air is 1.0006, which is rounded to 1. So therefore, a capacitor with air in the gap between its plates can be treated as having a vacuum between its plates. Now, as we said before, the capacitor stores electrical potential energy as there is potential difference between the plates, which causes attraction between the plates. So we have a positively charged plate where they've lost electrons and a negatively charged plate where they've gained electrons. Now, the greater the attraction, the more energy that can be stored by the capacitor. But remember, this is only true when electrons cannot move between the plates. So the attraction between the plates can be increased by the following. Increasing the area of the plate, as it allows more charge to be stored. Decreasing the space between the plates, as this will cause a greater interaction between the two plates. And increasing the dielectric constant of the material. The greater the insulation, the less likely it is that the charge will travel between the plates. Now this can be expressed mathematically by the following equation. C equals A times by E0 ER over D. Now A is the area of our plate in meters squared, D is the distance between the plates in meters, and ER is the relative permittivity. Now this equation can only be used for parallel plate capacitors. This tells us that the surface area of the plates and the capacitance are directly proportional, so C is directly proportional to A. That the distance between the plates and the capacitor are inversely proportional, or C is proportional to 1 over D. And then finally, the relative permittivity of the dielectric and the capacitance are proportional, so C is proportional to ER. So to summarise what we've looked at in today's lesson, we've looked at the concept of a parallel plate capacitor. We've looked at the idea of permittivity and that C is equal to E0A over D or equal to EA over D, where E is equal to ER times by E0. So if we've been successful and we've learnt in today's lesson, we should know the definition of relative permittivity and the dielectric constant. We should be able to calculate values of capacitance using dielectric action, and then we should also understand the effect of the capacitor dimensions in calculating capacitance. So thank you for watching this lesson on parallel plate capacitors, which is part of the capacitors topic in Module 6 Particle and Medical Physics of OCR A-Level Physics. Thank you so much and have a lovely day.